concept of time varying fields. As we already discussed upon, that time varying fields are completely different from the static fields, where the static fields follow other two laws like Coulomb's law and Gauss law or Biot-Savart law, such a concepts it will follow. And rather, in case of Faraday, so he developed the idea that when a current carrying conductor is available in a particular line and it always produces the magnetic field, this magnetic field will be perpendicular to both the line joining law. So this is Biot-Savart law. On the other hand, if there is a magnetic field which crosses the current uh, conductor, then we expect that it will produce the current, but it is not so. It's supposed to be time varying field. So this charge density is supposed to be time varying one. Then only this field will be uh, cut by the line and there produce the current, because the normal magnetic field with the static one, which is always which always has a loop upon that. So therefore, the net magnetic field produced for a given line is always zero. That is why there is no current. But in case of the time varying field, at any instantaneous time, the field is discontinuous. So which we always refer that as the line cut by the the magnetic field cut by the line, that comes the magnetic field. And by putting in a loop, then you can easily get the current which is driven. And if you collect that through battery or something, then you can generate current. So that is how electric generator works. And there comes the concept of uh, electromotive force. And this has many applications like transformers, generators, motors, and many other applications. Even in many sensors also it is being used. And later we have moved to Maxwell's equations. So in Maxwell's equations, we have seen the very important contradiction, that is displacement currents, which uh, which is one of the special case in the time varying fields. So these are the things we have seen last. And after that, we have studied the uh, electric and magnetic fields, how they behave in the materials, particularly the electric field. When you see that it give two important behaviors for conductor and the dielectric material. For conductor, we have a new phenomena called the conductivity, and now this conductivity also applicable to the dielectric material as well. And then inside the conductor and outside the conductor, all these things we already discussed about. And we move to dielectrics, and the dielectric is one of the material the uh, out of these two classifications, like metal and uh, dielectrics. We have the dielectrics, and under the dielectrics only all the other materials will come, at least in classical sense. There you got the semiconductors and so-called magnetic materials all the way. So that is all coming under dielectric materials only. So the dielectric material works with the phenomena of dipoles, and the dipole is going to induce the internal field. So that is always refer as dipole moment. In this accumulation of dipole moments, we will get a great field, and that field per volume charge will create a uh, pol yeah, charge density. That is going to produce a magnetic flux density. Sorry, the electric flux density. So that flux density we call that as a polarization. So it is very same as that of the electric flux density. And that is why actually we simply add the external field and the internal field, and which together when we add, we will get the total flux density. So this total flux density, we are going to uh, rearrange in such a way that a new quantity comes, that is a dielectric constant, which is arrived out of the polarizability of a material. And this polarizability depends on how fast it is moving all the way. So that describes various material properties like polar, non-polar, like that. And this dielectric constant, when this dielectric constant increases, obviously this conductivity, there is a huge relationship that this conductivity is very, very low for low dielectric constant, and this will gradually will increase by the way. So that is why the materials like silicon dioxide, which has 3.9, this is SiO2, which show a high insulating behavior. Rather, the titanium oxide, which show approximately 100, is highly conductive structures. So this also relate the link between this band gap. So this the electronic band gap also inversely proportional. So these theories proving themselves, they are complete. These are some of the external proofs we have that the electromagnetic field theory is complete theory, that it can prove itself correct. In fact, Maxwell's equation is always questioning about the completeness of its own. Okay, so next we are actually moving towards the further more material properties upon the electric and magnetic fields itself. So in case of the material, it is further divided into three. One is linear material. Of course, we can easily understand that the electric and magnetic, the flux and the field, they will be linearly linked. Therefore, the conductivity or the dielectric constant will be constant, and they won't vary with respect to the material space. So they are called for the applied field. So they are often referred as linear material. But as of now, there is no linear material available in the world as of now, it's predicted, because always this dielectric constant is subject to electric field. So that is why if you take any capacitor with respect to the applied voltage, there will be a slight increase will be there. And this increase often consider some of the error source of the present day electronic circuits. And then homogeneity. It is assumed that throughout the material space, the dielectric material will be uniform. So that is nothing but homogeneous. And that is also subject to question in terms of the real world. And if we have multiple materials layered, they will be called as inhomogeneous material. And later we have the material called isotropic. In this isotropic, this dielectric constant and this one does not vary in any particular direction. So that is called isotropic material. So for instance, if you take the silicon carbide has two lattice behaviors. In one particular direction, it will be having one particular concept, and in another y direction, let's say, it will be having different lattice lengths, which we call interatomic distance. So because of that, this their corresponding the elastic property is also different. Thereby, the dielectric constant in one direction it will be different, in another direction it will be completely different. So this often used to estimate the behavior of the isotropicness of some other material. Because if there is a material is isotropic, then it is relative to this silicon carbide, we can easily evaluate it. This is how actually it is described. Upon this, we can find still the link between this, the seemingly look like independent properties like conductivity and dielectric constant. We can relate by the time and space itself. Often comes under the concept called continuity equation. This continuity equation being derived long back itself. There is a still debate who started this continuity equation. Perhaps in the some of the works of Euler, we can find the continuity that if your water is going in a particular speed in a tube, let's say, then without any blocking, simply it is traveling. Then at any particular cross section view, then the total current, water current, which is J, is directly proportional to the velocity of the particles whichever is moving in. So that is what he referred, where the velocity is bringing in with respect to the particle. So as a whole, we call that as a current. As individual, we are calling with the particle with the velocity. So according to Euler, the both are same, which is true with respect to the fundamental nature of the structure, and that is what we call the conservation. The law of conservation also agree upon that. So the same thing we can apply for the current, the charges also. When the charge is actually moving in a particular space or a particular medium, then in a given closed surface, if you take, then obviously the total current density, which is equal to the total charge moving in a particular velocity. So here d by dt can be nothing but the differential term which describe the rate of change of the charge density, the charge which is moving in. Of course, this is the first, this itself fundamental statement of description of current itself. And the current, we can say that it is integration of the current over the closed surface, which is nothing but minus dq. And this minus sign, always we refer this with the force which is exactly opposite to the field, whatever is tuned with. Later, I think it will be called as Fick's law, I think. Now, we can apply the divergence theorem as well as Stokes theorem on both the sides, and then we can easily get the link between the two cases, the conductivity and the dielectric constant itself. So for this expression, which has the surface charge, surface integration, can be converted to volume integration by applying the divergence theorem. So when you do that, you will get this equation in the left hand side, and in the right hand side we have the change in the charge or total charge with respect to time, where charge is nothing but the integration, volume integration of the charge density. So the operator is available in the outside of the total Q. And if we consider the material is linear, homogeneous, as well as isotropic, then this differential operator, this volume integration can be linear as well. Since it is linear, we can take this differential equation inside. Sorry, the differential operator we can bring inside, and we got this. Now this is actually left-hand side, and this is right-hand side. Both supposed to be equal. Thereby, we can cancel out the linear integrations on both sides. Linear integration means this the with respect to space, this material is linear, homogeneous. So all the way, the same type of integration is going to be applied. That is why we can call them as a linear integration, and thereby we can cancel out that. If there is no, if there are three different materials, we can't apply this continuity expression. And so there, when we compare this two, we will get the equation. This equation, one of its first of its kind, that describes the current, which is actually described in the space, and the same current is described in time. So in fact, continuity equation would be the very starting point of several important theories, including this semiconductor, where we find diffusion current, which in fact properly described by Flick there, where they have introduced to one more constant called diffusion constant. I think that is done by Einstein. Later, it is originally introduced into the semiconductor equation, that is current transport equation by Langevin. So both are important people in the field of semiconductors. And also the same expression Einstein later used in special theory of relativity. So here we are assuming this, there is no observer. If you put an observer, then you will get the theory of relativity. So this is a very important expression. And in this equation, we're supposed to keep in mind a few things, that the so-called the principle of conservation or the law of conservation, it states that there is no so-called accumulation of charges. The flow is whatever that is charges are coming into the surface is excited out. So thereby there is no accumulation. And if this, so this is we have to keep in mind. And this sometimes may not be true for the surfaces. Surfaces means there are two materials, one material with dielectric constant 1, another material with dielectric constant 2 or something. In that case, uh, this field, the D and this D both are not same. If it is so, then the charge density also supposed to be not same. This is charge density 1, and if they are not same, then there will be a question of continuity. That is where this we have to keep this in mind. Next, the current, if there is a static current or steady state current, which means the change in charge density with respect to time is 0, then we will get this expression. This is what we always apply for many important equation, and this Kirchhoff's law also following the same pattern as well. So I already told about that during the time of Maxwell, Kirchhoff was also there. In fact, he largely inspired by Maxwell's work itself. It seems like I think so. Kirchhoff is elder than Maxwell, but generously he has considered some important works of Maxwell, and of course, I think just after Ampere, he started his work, I think. Now, we have two important equations. One is Ohm's law, another one is Gauss law. And these two, when you substitute one on another, then you will get interesting behavior. So what is that? So we have this J equal to sigma E. And if we substitute this equation, let's say this equation number 1 in this expression, then you will get del dot sigma E will come. And since it is a linear material, sigma can be taken out, and we will get sigma del dot E will come. So I believe you can easily understand that. So we got this expression, and this sigma we can take it out since it is a linear material, which means throughout the space we will get same behavior. This also correct, and the sigma del E also correct. So we got sigma del E, which is equal to just a minute. Yeah, okay. Dot E. Okay. So yeah, here we get this equal to, yeah, this electric field is equal to J by sigma, and this when we substitute here, we will get del dot J by sigma is equal to rho v epsilon. So this sigma can be brought this side. We will get del dot J equal to rho, sigma rho v by epsilon. So this equation, what we see here, and which is actually equal to minus rho v by dou t, which is according to the continuity equation. The continuity equation is connected with this. Now we are going to solve this expression. So in order to solve that, we have to integrate with respect to time. When you integrate with respect to time, you will get this one. So ln of rho v equal to minus sigma t epsilon into ln of rho naught, where rho naught is nothing but the initial condition, or the at time t equal to 0, the total charge density available. So this itself is stating that if you keep a charge density at time t equal to 0, and later after time, let's say after few moment, then you won't get the same charge density. So this is the charge itself is time dependent one. So by rearranging this expression, you will get the charge density with respect to time itself. So what this indicate that in a, let's say there is a charge is accumulated over a particular material at 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 a space x equal to 0, then the charge is actually huge amount of charges is accumulated here. due to some injection or some other maybe. So we have inserted charges and the charge is available over the space. After time, few moment later, this charge will start to move along the space. And this moment is which we call diffusion. And that is very early day itself being described. And so this makes the exponential decay of the charge density with respect to the time. And this process will keep on happen till this charge density will become uniform throughout the space. And so that will take a huge amount of time. But in order to define this, uh, uh, the rate of movement of the charges with respect to the time, there is a new factor being introduced that is called relaxation time. This relaxation time is nothing but epsilon by sigma. So this is one of the very important description relating the dielectric constant and the conductivity of a particular material. So it is very important to evaluate the value. So for this exponential term, when it is reduced by 60% of that, sorry, 36% of that, then we will get the value of one moment. That is which we call relaxation time. And this relaxation time is one of the very important quantity largely being observed in both conductor as well as uh, the uh, the dielectric materials. In case of conductor, we know that they will be having very high conductivity. Since it is inversely proportional, the time will be very small. For instance, if you take the copper has the highest conductivity of approximately 5.8 in 10 to the power 7, and its dielectric constant is 1 since it is a uniformly charged metal. Okay. Uh, there is no so-called definition for dielectric constant, or no, there is no dipole. That is why the dielectric constant will become 1. So when you substitute all these values, you will get the value of 10 power minus 19, which means that let's say you take a copper, then you are actually introducing electrons inside. This side is completely grounded, which means the surface potential is 0 itself. Then the moment it comes inside the copper conductor, then at no time, at least within about 10 power minus 19 seconds itself, this charge will be available almost everywhere and almost uniform throughout um, the metal space itself. So this is the time will take to disperse or diffuse over that. This is why actually conductor looks like very fastly. Means the electron goes much fast inside the conductor. And when you apply this fused quartz, that is nothing but silicon dioxide with which is fused with very huge amount of time. That means it's silicon and oxygen are bonded properly, and it is highly transparent as well. So, and that material has very low conductivity. Of course, it is very well, we can understand that when there is a proper crystalline, then we will get very huge uh, band gap. Therefore, the electron cannot go from valence band to conduction band. And therefore, the conductivity also very low. It is about 10 power minus 17. So it is a highly insulating material. When we substitute this in the for the calculation of relaxation time, it comes around 51.2 days, which means that much time it will take to move from one place to another place. It is very huge. So this quartz can be largely used for many applications like protecting the like protecting some like electronic structures with a transparent cover for that purpose, as well as for uh, heat resistance applications. Many places it is used. These are the things we can get relationship between the material. And so for this all describes, including this dielectric properties or the conductivity of metal all the way. So these all describe a homogeneous medium, which means that throughout the space, only one particular material will be available. But in reality, so many applications will be carrying sandwich of materials or multiple layers, and these layers will be sharing one common boundary, which we call interfaces. So at these properties, how this dielectric, uh, uh, the fields, how these fields will behave. Will the field will be same throughout the material space? For example, here it is dielectric constant 1, and here it is dielectric constant 2, and here it is dielectric constant 3, like that. In that case, uh, will we have this electric field will be uniform throughout the space or not? And if it is not, then what could be the reason for that? All these things we can study. And this is applied in multiple fields, not only one field. Like here it is shown with a MOSFET. I believe all of you know about MOSFET. So this is applied to only semiconductor device here. But you can apply for many fields. For instance, if you take the Earth has uh, uh, silicon dioxide here. However, it is also has a huge amount of metallic particles. Therefore, it has the very high conductivity. And because of this high conductivity, when there is a electric field is hitting upon that, then some amount of electric field will be reflected back. Some amount of electric field will go inside. And this penetration depth also we can even calculate. And this is interestingly applicable for one particular frequency. For another frequency, another depth will be there. So using this property, we can study the conductivity of a particular material. And so in order to get huge amount of reflections, you need to get very high conductivity. Sometimes for radio wave communications, so to stop the electric field to go further inside upon the some of the mines, they place some metal wires on the top. So so many engineering works being developed upon the this particular property, that is boundary, means the boundary theory for the electromagnetic fields. So and to analyze this calculations upon this electric field, whether it is continuous or not, whether it is uniform throughout that E1 is equal to E2 or not, to check out these all, we have a condition, and that is often referred as boundary conditions. So this boundary condition is very useful one. If you know this E1, and by knowing the value of the dielectric constant of these materials, we can calculate the E2, and thereby we can calculate this E3. And you should remember that for a semiconductor device, in order to calculate the current flow, let's say from source to drain, we need to calculate the charge density, and this charge density can be calculated after calculating these electric fields. So that is the general flow. So this electric field, if we calculate wrongly, obviously the charge density will be wrong, and we can't get the correct current flow. Thereby, we can't design the device itself properly. So not only this application, so many applications we need this kind of boundary conditions to be addressed. This further divided with 4 categories, and today we are going to see the first of its kind, that is the dielectric interface. If there are two dielectric material commonly share a boundary, and if the field is traveling from one material to another material, and what about the electric field? Will it be same in both the material, or will there be any change? Of course, we know that there will be a change, but there are some interesting phenomena will make it same as well. We will see what is that. So in order to study this particular boundary conditions, we are going to assume that a field is traveling from one medium to another medium, and this medium has the first medium 1 has dielectric constant 1, and medium 2 has dielectric constant 2, and a field is traveling with a magnitude of E1, which is traveling over and crossing the boundary and traveling to another. So in order to distinguish, we are going to say this electric field at medium 1 is E1, and here at E2. And to study the basic nature with respect to the three-dimensional space, we are going to divide this into two vectors. One is called the tangential vector, another one is called normal vector. So the same E1 will be having two components, and these components largely produced with respect to the normal to the surface. So here we have the surface, which is the boundary, and this boundary has the normal vector. Okay, so for example, this is completely curved one. So in every place there will be different normal vectors will be available. If the boundary is a straight line, we will be having same normal vector. For instance, with respect to this, we can say that the normal vector is AZ vector. So how to calculate this normal vector and this normal component and the tangential component? First, we have to calculate the normal to the surface. Then if we multiply this with the electric field. So this is the electric field, which is defined with respect to x, y, z axis. Three vectors are there. When you take the dot product with the corresponding normal vector, then you will get only the magnitude of the normal component. You can call it as En. And this En, if you put this vector, normal vector, then you will get the normal component you got, and the remaining all nothing but the tangential component. This is how we have to divide that. When we take some example, you will really understand that. And these two components, when you add together, you will get the E1, and the same thing applicable to E2 also. Now the question is, when the tangential component and these two, what is the relationship? So in order to do this, we have to apply certain conditions in the boundary, and that is directly we can take it from the Maxwell's equations itself. So how to apply up this? So we have two theories. One is in a particular loop, if we calculate the total electric field, it is always going to be 0, because the electric field is always converging or diverging, so which you can't accommodate within the closed loop itself. And then we have second theory that the integration of the overall exerted electric flux is going to be the total charge available here. So that is why we call this D is equal to the charge density itself. Thereby, so in order to do this, we need a closed loop. And in order to do this, we need open surface. So these two things needed. So for doing this, in the common practice is people always draw a closed loop which will cover both the regions. So you can see that there is a closed loop which has A, B, C, D, and the current is, there is a field is actually flowing in both the directions. And to describe the loop, we have these arrow marks. So it is going from A to B, C, D, and again it's come back to A. And this has its own width and height. So its width is a small width del W and a height of del H. Now what we are going to do, if there is a electric field is traveling from medium 1 to medium 2 as E1 and E2, then if we apply this closed loop, here you will, for this 1, 2, 3, for this 3 loops, we will take this E2 vector, and for this 3 loops we will get E1 vector, and according to the loop, when we add all of them, we are supposed to get 0. Therefore, we can get the link between this E1 and E2, at least in terms of tangential or normal component. And by comparing that, we will get the understanding whether this and the relationship between the E1 and E2, and that is described with the dielectric properties E1 and E2. So let's, and same method for a closed surface integration, people always take a common surface. Here it is given with some cylinder. You can also take some rectangle box. Okay, so this often referred as pill box. And so when you do this integration over the open surface, then you can calculate the normal and tangential component. by integrating them, you will get the relationship with respect to charge density. Charge density is relevant with the conductivity of the material, and thereby we can relate it. So let us take the first condition, that is dielectric interface. There are two dielectric materials, and one has the dielectric constant of the epsilon. Sorry. Yeah. One has the dielectric constant of epsilon, and another one is the dielectric constant epsilon 2. And here it is defined. Now, electric field is traveling from medium 1 to 2, and their corresponding tangential and normal components are written. And this component we are going to apply for a closed loop. So the closed loop is defined here. So to start with the medium one, so it is start with A, B, C, D like that. Now this is actually a small del W, and which we can call it as DL. So this DL, it has its own vector. So this is going to be along the tangential component, and this is going to be the normal component. So we can easily say that this A to B, we will get only tangential component. The corresponding multiplication with the normal component, obviously it is going to be 0. So by this way you can split two components. And what about the normal component? It will be available only for this BC and this DA lines alone. So that is how the integration always will result 0, which is equal to this first tangential component 1 with del W. So this one, and up to half of that we got the normal component, the second normal component here, and the tangential component another. So there will be about totally 6 components will come out of it. So we have written all of them. And so first one is with respect to width, and the remaining 4 are nothing but half of the normal components. So you can easily see that these components they have written with respect to the del W and del H. Now what we are going to do, in order to calculate exactly at the boundary what is the value of E1 and E2. So in order to do that, people always make this del H equal to 0. So if the del H is equal to 0, then means we will get the exact boundary. So by doing this, we can say that all these components will become 0, and therefore we will get this condition. And del W we can take common outside, which is not at 0, and thereby we will get anyway this del W later becomes 0 by stating this, and therefore we will get this equation. So this equation says that we have a boundary, and this boundary defined by two materials. Okay, this is completely different material, and this is completely different material. When the field is traveling from one medium to another medium, E1 and E2, and in this we have tangential components. Okay, at present we don't worry about normal component. We have two tangential component and two normal components. In this tangential component E2T, so both are equal, which means that the tangential component, they are not going to be affected by this change of boundary. So one can easily think about, since the dielectric constant is different, there are supposed to be a discontinuity upon the field components, but that is not true. So the tangential component will survive, and the same tangential component will be available. This is the same thing applicable to this air medium and the ground. The tangential component will not be affected. The tangential component simply will penetrate the ground, and it will go inside. But if you keep any normal component, that is not so. The normal component generally will be reflected because of the change of the dielectric constant from air medium to ground. So it is often referred the condition as the tangential component of electric field is always continuous. And what about the same corresponding component in terms of the flux density? So the flux density in the medium 1 and medium 2 we can define, and corresponding tangential components are taken, and according to this equation, that is condition 1, this equation is true. Therefore if you substitute this with d T1 divided by epsilon 1, same thing for this, you will get this equation. And according to this d is not equal to this d because they are actually divided with the delta. So therefore the tangential components of the flux density is not continuous, which means you won't get the same value, and this is true. And this while the electric field is same, but the flux density which are corresponds to the volume charge density of the material is not same. So there we can link with the Gauss law. So Gauss law states that if you take the surface integration over a region, then over a closed surface, sorry, over a closed surface, then you will get the total charge density. And so in order to do that, we are actually taking a pill box. The pill box has a surface area and it has the height. Now we are applying the same component, and finally we are going to take this del h equal to 0. If you make the del h equal to 0, then you will get only this charge density. By the way, you can calculate the you will get the total charge. Thereby you can calculate the charge density, which is supposed to be nothing but the difference of this two mediums. You will see that the surface component has this normal component here, and this side we have this normal component. So since the normal component alone available and the radical component we can't multiply with the tangential component, anyway it is going to be 0. So the normal component alone will survive. So you will get this d component, and when you subtract this 2, you will get it. So this is the normal components, which is equal to 0. This clearly says that the normal components of the flux density is not going to be continuous. It is highly depends on the charge density of the medium, at least in the surface. If the surface has some charge density, then you won't get the fields on the both sides. At least in the normal component, you won't get it. So this is the condition 2. So the normal component of the flux, they are actually discontinuous. And there is a special case that if both the dielectric materials are completely insulators, there is a chance of having this dielectric constant, this charge density will be equal to 0, and you will get the normal components, both will be continuous. And this is applicable only for the dielectric material has no charge carriers, often referred with no free charge carriers, no free charges. And finally, we will get d1 the d1n equal to dn2 will come, and this will, if we expand with respect to the dielectric constant, we will get this e, let's say e2n is equal to e1n divided by this epsilon 2 epsilon 1. So there clearly it says that since these two values are not equal, obviously E1 and E2 completely different. By the way, we will get these two. So from this we got important things. We have components like E1, E2, D1 and D2, and they are actually related with two materials. And when the tangential components of the electric fields are equal, while the normal components are not, and here the normal components are uniform, and in case if the charge density is 0 and the tangential component is not equal. So by the way, you can easily say that for electric field, tangential components are continuous, normal components are discontinuous. For flux density or the relative charge density, which is connected with the conductivity, there comes the normal components are continuous and the tangential components are discontinuous. Like that, these are the boundary conditions. So these conditions would be very helpful to calculate the electric field present in the second material due to the electric field in the first material. So here the priority or the requirement or the minimum known values are nothing but the field at the medium 1 and the two dielectric material properties. Therefore, you can calculate this third one, and the remaining things can be calculated by finding the difference. We can get the charge density itself. Surface charge density can be found. Recently, it been found Recently means in about 30 years back, one interesting phenomena been understood, that if you take silicon dioxide and another material, let's say aluminum oxide, like that, so both are highly insulating material. Okay. One is has the dielectric constant of 3.9 and this has dielectric constant of 10, 9.9 something like that will come, so we can take it as a 10. So this we can take it as a 4. Both are highly different. And if we put two electrodes and both the electrodes are connected with battery, now we will see that the electric field will form. Of course, we know that here electric field 1, here electric field 2. According to this, the normal components alone will be available. We know that the normal components are not same. In that case, to make the state of the or to make this entire system stable, there will be some surface charges will be accumulated naturally. So because of that, if you calculate the if you keep on increase the electric field, so when you increase this, the capacitor value will suddenly increase, and after breakdown it will start to discharge. So this behavior you can find it in many capacitors, particularly this kind of sandwiched materials. And this is this kind of accumulation of charges often referred as Maxwell-Wagner polarization. This Wagner, actually, he is one of the important person in the field theory, particularly in the state of material, and he is, I think, student of Langevin, and he immediately wrote the expression for the charge density which is accumulated here. And so this clearly states that the continuity equation for the this continuity equation for the field theory first wrote by, I think, Langevin, and that immediately his student followed and understood this idea. And this one is actually very useful phenomena. So if you take a material which has very low dielectric constant, let's say I have a air medium and then silicon dioxide. So I have silicon dioxide, air medium, silicon dioxide, air medium. So this is silicon dioxide and another air medium, silicon dioxide and air, and then another silicon dioxide. If you keep that, it look like these materials are having 4, 1, 4, 1, 4, 1, look like that. But the moment you apply the voltage, which makes the field distribution, the charge in the interfaces charge density will be very high, which will result in the total effective dielectric constant. Sometimes it will go greater than 1000. So by this way, one can easily increase the dielectric constant of a particular material. So this recently applied in some of the transistors. So they have put multiple sandwich of material. Therefore, the effective dielectric constant is reaching approximately 800, like that. And if you put a normal material, it is going to show 4, which is silicon dioxide. But due to this metal property, we get 4, which means that it is about 200 times higher. And I think everyone knows that the current is directly proportional to the dielectric constant of this oxide material. So by the way, current will increase by several times, at least 100 times the current will increase in reality. So this is one of the recent works going in the nanoelectronics to increase the current of a particular device. So by the way, if you can increase by 100 times, the total width of the device can be reduced by 100 times. So by the way, you get a reduction of size in the third dimension. People generally work in the x-axis and y-axis. For the first time, people started to work in the z-axis as well, along the width side. So this is one of the simple application we can easily understand from this boundary conditions. There are many things we can do, and some other interesting cases we are going to study in the next class. Have any questions?